Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about big O notation. Let's get started. So we are given a function to solve a problem, and the expression of time taken by this function to solve a problem is given by 2n plus 3, and we have to find the order of growth of this function. So what we do? We use the direct method to get the order of growth of this function. I talked about direct method in asymptotic analysis track. So if you don't know about the direct method, you can simply go to asymptotic analysis track and watch that video first and then come back here. So what direct method says, ignore the lower order term, ignore the coefficient of higher order term, and you get the order of growth of this function. So we cancel out the 3, we cancel out 2, and we get the order of growth of this function as n. And we call it big O of n, because in this expression the higher growing term is n only. So that's why the upper bound of this function is going to be big O of n. So this is the direct method to find the upper bound of a function. Now in this video we are going to see how to prove it mathematically. So let's see it. So we have a function and the expression of time taken by function is given by 2n plus 3, all clear, and we have figured out that the order of growth of this function is big O of n. So here, what is n? So n is nothing but the expression of upper bound, right? So in terms of function, we can write it like gn is equal to n. Okay? And we have proved recently that function f of n is equal to big O of n. And now I can substitute the value of n as gn. So we can say that the function n is big O of gn. So theoretically we have proved it. But mathematically, this is only true if there exists some positive constant and n naught such that function f of n is less than or equal to cn for all n is greater than n naught. So what does it mean? We can say that fn is big O of gn only if there exists a positive constant and n naught. So we have to find n naught and positive constant such that fn is less than c of gn for all n greater than 0. So let's understand this with an example. So fn is equal to 2n plus 3. We already have this expression. We have this statement also, gn is equal to n. If we want to say that fn is big O of gn, then we have to prove that fn is less than or equal to gn. So let's put the value of fn here. So fn is going to be 2n plus 3, okay, less than or equal to c of gn. Correct? We are using this statement right here. And now, the value of gn is what? We have calculated here. The value of gn is n. Because n is the expression of the upper bound, we can write it in terms of function as gn. So we put the value of gn as n. Now we have to figure out some value of c such that 2n plus 3 is less than or equal to cn. So how to get the value of c here? See, this is a simple trick. If we want this expression to be less than this expression, then we need some value which makes this expression greater than this expression, right? So let's use a simple trick here. See, the growing term in this expression is n and the coefficient of this n is 2. So let's take the 2 and add 1 to it. So it becomes 3. So let's say c is equal to 3. And why we are taking c? Because we ultimately want to make this expression smaller than this expression. So that's why we take 3 as a constant. So now let's put the value of 3 here. It becomes 2n plus 3 less than or equal to 3n. Okay? And then it becomes 3 less than 3n minus 1, and we ultimately get the value of n greater than or equal to 3. So we get the value of 3 and we get the value of c also. So our c is equal to 3 and n is equal to 0. And n naught is equal to 3. So now let's again put both the values in this expression. So 2n plus 3 is less than or equal to 3n. Let's put the value of n. N is 3. 2 into 3 plus 3 less than or equal to 3 into 3. So see, the LHS is equal to RHS. So we have proved basically that this expression is true, or this expression is going to be true if the value of c is going to be 3 and the value of n naught is going to be 3. Okay, let's take the value of n equal to 4. So if I take n equal to 4, then also it's going to be true. Let's see. 2 into 4 plus 3 is 11 and 3 into 4 is going to be 12. So 11 is also less than 12. Okay, now let's take the value n is equal to 2, which is less than 3. Okay, so if you put the value n as 2, 2 into 2 plus 3 is equal to 7, and 3 into 2 is going to be 6. So it fails to prove that fn is big O of g. As per our mathematical proof, we conclude that the n naught is going to be greater than or equal to 3 always, and the value of c is going to be 3, such that fn is always less than c into gn. And based on this value, we can say that the function f of n is equal to big O of gn. And if I show you on a graph, then you can see that this line is our function fn, and the expression is 2n plus 1, and this line is going to be g of n, that is 3n, and this is our intersecting point, and the value of this intersection point is 3. So when n naught is less than 3, it seems like gn is growing slower than fn, but when we put or when we give input greater than or equal to 3, then we can say that the gn is growing faster than fn. So that's why we are calling that the gn is the upper bound of the fn, and mathematically also we proved it, that if we put the value of c as 3 and n naught as 3, then this expression is going to be then this statement is going to be satisfied. So now talk about when to use big O notation. So there are scenarios where it is very difficult to know the exact bound of the function. Because of the complexity or so many business logic, it's difficult to tell the exact bound of the algorithm or function. So in those cases, you can use big O notation, because big O notation covers all the cases, from the best case, from the average case. So generally, we are normally interested to know about the big O notation only. The reason is it gives the upper bound of a function. It means if I tell that the order of growth of any function is n in worst case, so it means the function is not going to grow more than n. It's always going to grow in order of n or less than order of n. And this way we can easily determine that which algorithm is growing faster and which algorithm is growing slower. So use big O notation when you do not know the exact bound of the function or algorithm. So this is it about big O notation. Thanks for watching. See you in the next video.